Can't make the test too easy. All right. Yeah.
I'm so confused on that. L is decidable, and then it puts L complement.
No, I'm saying I give you an arbitrary decidable language, then give the most restrictive class for L bar. Okay?
Can we do a Rice's theorem?
Sure.
There's a 5.
Well, we can go to Panda Express. Rice puns. All right.
I'm sorry, I did that.
Any example?
So from 530 on 341, there's a M is machine M is a TM, and
1011s and one, yeah.
Yeah.
So yeah, I know that example because it's in my solution manual on GitHub. All right, so
And it's not on the test, right?
no. Okay, so this is decidable. It's not decidable. Well, could I prove this using Rice's theorem? Yeah, well, is the language consisting entirely of single machine encodings? Yeah, so that doesn't mean we can apply Rice's theorem, it's just that we can't immediately throw it away. Okay, well, if I want to use Rice's theorem, what do we need to show? That it's a non-trivial property of Turing machine languages. So ignore non-trivial for a second. So can we show that it's a property of TM langs? Yeah, how would I show that? Well, yeah, I have to show you have two arbitrary machines with the same language. Arbitrary machines. So if L of M1 equals L of M2 for arbitrary M1, M2, could it be the case that M1 is an L and M2 is not? No, because they have the same language. Then either 1011 is in both langs or neither. Yep. Super. And then we got to show it is non-trivial. Yeah.
Is there ever a situation where the property of Turing machine languages doesn't apply when trying to get Rice's theorem?
Yes. If I add the extra condition that M has at least 5 states, in addition to having 1011, then it could be the case that they have the same language, but one has
6 states and the other has 5 states.
Yeah.
Oh, okay.
Yeah. So if it only deals with the language, then you can apply the property part. Okay. Non-trivial. What do we need to show? Right. I need to show some machine in L and another machine that isn't in L. Any example? Yeah. So let A be ATM that accepts nothing. Therefore, A's description is in L. And then what's one, no, it's not in L, thank you. What's one that is in L?
Only accepts 1011.
Yeah, so there are many examples you can pick. So B, ATM that accepts only 1011. Then we know that B is in L. Are we done? By Rice's theorem, thanks. So by Rice's theorem, L is undecidable. Okay. Other questions?
do want that we have to be within the tier middle view. We have to draw the transition for the tier machine.
You won't be asked that.
You're not gonna ask us that?
What was the version?
Draw a transition diagram of a Turing machine.
Like the one underneath the two?
Yeah, that'd be ridiculous. Think of me. I have to grade these within 2 days.
Okay, thank you.
I mean, I could kill myself to do it, but
Okay, thank you.
Yep. But the idea of how the Turing machine actually performs and like what it's doing, like writing on every single transition and moving left or right only, that's important. Yeah. Okay. Other questions?
I'm sure people on Monday might have questions.
Might?
Should have questions. Hopefully have questions.
Can we do something similar to the mixing decidability from,
Oh, you said 4?
yeah, you said 4. Sorry, I don't have any.
Okay. So this is an exercise in the book, but I might as well do it here. Oh, no, that's fine. Okay, so you're given a grammar and with alphabet 0, 1, and you have to figure out whether or not it only accepts strings that have no zeros in them. Okay? So every string that it accepts has only ones in them. Okay? And I claim that this is decidable. So if I want to make a decider for it, how should I start off? On input G. Good. So on input G, where G is a CFG. Well, how could I check that the language is a subset of 1 star? If I happen to ask, what is 1 star the most restrictive class for 1 star, what is it? Yep, it's regular because it's a regular expression. So, okay, so we have to determine if a grammar's language is a subset of a regular language. How could we do that? But there may be unreachable transitions on 0 or unnecessary transitions on 0, right? So how do I write in another way, A is a subset of B? What's another way I can write that? There better be nothing that's in A and outside of B. Right? If it really is a subset, there's no way there's nothing in A that's also outside of B. How do I determine what outside of B is? The complement of 1 star, or B in this case. And it's also in A. So A intersect B star, B complement. And what do I better hope that be? Empty. Okay, well, let's see. So let's see. What does a context-free language intersect a regular language? Context-free. Because how do we know that? Context-free languages are not closed in an intersection. Yeah, they are closed with regular languages.
Yeah, my bad.
So how do we know that that's true? Because it was one of the extra questions on the homework, and another one for CFGs. And if you want to do it with PDAs, you do a product construction with DFAs. So a PDA and a DFA, and the transitions, whatever you do with the stack is what the PDA would have normally done. Okay? So, well, that's working with PDAs, and I'm given a CFG. Is all hope lost? Oh, I can convert it to a PDA. So, convert G into an equivalent PDA P. Okay, now what? What do I do here? Well, I want to make a CFG or PDA for that guy. A intersect B complement. Well, what is A in this case? It's the language of the grammar or PDA here. What is B here? 1 star. Good. So construct a PDA. Let's call it P prime for L of P intersect 1 star complement. Could I check whether a PDA or CFG's language is empty? Well, we have a decider for what though? We only described one for CFGs. We didn't describe one for PDAs, but is that a problem? No, what can I do? Convert it back. Good. So convert P prime into an equivalent CFG G prime. Well, how do I determine whether or not G prime's language is empty or not? Perfect. So run the decider for ECFG on G prime.
And it has to be included.
Yeah, because we have to feed a string to the machine. Yeah. Well, can the decider, let's call it D, can the decider D run forever? No. So don't say on the test, if the decider runs forever, because I hate when that happens. If D accepts versus if D rejects. If D accepts and says, yeah, G prime's language is empty, we should accept because we just determined this condition that it's empty, but that means it's a subset. So then just accept. And then for rejects, it's pretty obvious we'll reject here. Okay. Yeah, I like these problems because they combine so many ideas of the class into one problem. why I put them on homeworks. Other questions? So I'm pretty confident there's not a single part of the class that won't be tested in some way. So either only a tiny bit or a lot. But it'll try to be as even as possible because I can only do so much with 9 questions. So.
Can you tell us if there's any like diagrams that we're like the state diagrams? I mean, I know we don't have to make
I
a
can't
determination.
verify or deny that
Okay.
statement.
Okay. I mean, that's better than nothing.
Assume, yes.
Will we have to do both versions of the pumping though, or just one?
If I have a single language and I say, show it's not regular and show it's not context free, what should you do? Show it's not context free, and for the other part? Yeah, it's not context free, so therefore it's not regular. Yeah. Other questions?
Is roller coaster tycoon really your favorite game?
It's one of my favorites.
Okay.
Top 5?
It is, yeah, it's one of my, I actually still play it. It's yeah. There's another sim game called No Limits, Roller Coaster Simulation, which allow for a lot greater precision in terms of what you can actually make. So instead of this blocky type thing, so I highly recommend checking that out. But Roller Coaster Tycoon is really great. Yeah.
How do you have time to be a computer scientist, a musician, and a gamer? You're a musician too?
So you know that triangle diagram where it says pick 2 of these, like social life, sleep, and good grades? I just axe social life away. And so I have 2 left, I just pick those. Yeah.
So sleep and good grades.
Yeah.
Wait, you said you played sax.
It's on,
Oh,
it's on YouTube.
Mm-hmm.
There's a picture of it on his YouTube page. Right.
Yep.
I don't
Violated sax.
I was watching
Your violated sax is very much the same.
Yeah. The intersection's empty. I don't know, there may be someone who does both, but yeah.
So can we do a small power set?
Okay, yeah. We haven't done one of those in a while. That's good. How about let's take the NFA we had before way up here. And you'll get to see all the cool stuff that I research on Monday, so I hope that'll be interesting at least. Okay, yeah, I think this is sufficiently good. Oh yeah, thank you.
We're doing a power set construction?
Yeah, a power set construction. Okay, so, well, the alphabet's obviously A, B here. So, what should I do first if I want to convert this to a DFA?
Oh, yeah.
What thing do I need to look at first? Well, the start state, but what of the start state do I need to look at? The something closure,
Oh, that's
epsilon closure.
Yeah.
What is the epsilon closure of just Q0? Just a self. Okay, that's good. So I make a state just Q0, which is the start state. On input on A, where can I go from Q0? Q1. Be careful. Can I go to Q2 from Q0 on input A? No. So the states that I have currently listed are Q1. Now what do I look at? Epsilon closure. What is the epsilon closure of Q1? Q1 and Q2. and that's it. So then I make a transition there. Now what? What else could I read from Q0? B. Oh, where can I go on input B? Empty. Yep. So I make a new state, empty set. What does empty set do? It loops on all inputs because it needs to be a DFA. All right, Q1 and Q2. Where do I go on input A from Q1 or Q2? Q0 and Q2. So Q0, Q2. Where does Q1 go on A? It goes nowhere on input A because there's no transition on input A. So I have Q0 and Q2 listed. What is the epsilon closure of Q0, Q2? Itself. And I don't have that state already, so I make a new state. Q1, Q2, where can I go on input B? Well, where does Q1 go? Itself? Fine, so I have Q1 so far. Where does Q2 go on B? Q1. Okay, so the only thing I have so far is Q1. What's the epsilon closure of Q1? Q1, Q2. Oh, do I have that state already? Yes. So I make self-loop. Almost home free. Q0, Q2, where can I go on input A? Actually, we're kind of far. Never mind. Q0, where can I go on A? Q1. Ignore Q2 for a second. Q2 on A, where can I go? Yeah, itself or Q0. So I gotta make, and those are all the states, so I don't even need to check epsilon closure. Q0, Q2 on B, where do I go? Q0 goes to where on B? Nowhere. Where does Q2 go on B? Goes to Q1? Oh, sorry. Yeah, okay, Q1, fine. So what is the epsilon closure of Q1? Q1, yeah. So I come back to Q1, Q2. Q0, Q1, Q2, where can I go on A? Well, Q0, let's make a list. Q0 goes to Q1. Q1 goes where on A? Nowhere, good. Where does Q2 go on A? Itself and, yep. So therefore I make a self loop. What about on B? Yep, so I have Q1 on my list. Where else? Just Q1. What's the epsilon closure of Q1? Q1 and Q2. So I do that. Now, what do I do? Final states. So what are my final states going to be? Everything that has Q0 in it. Yep, so that guy's final, that guy is final, that guy is final. Sweet. Any last minute questions? Like literally last minute. Okay, see you Monday.